Hello and good evening. I think it's the 8th episode of Anglo-Irish Astro Geeks. Our co-hosts and our guests have had a great time getting to know each other beforehand, so we'll get started. So my name's Nick Yvetz.
I'm Anne Dunn from Astronomy Ireland.
I'm Susan McKeown from Dublin, Ireland.
I'm Neil Norman.
And our guest.
I'm Kim Page, visiting for this one.
Welcome to the show, Kim. Great to have you here.
Thank you.
So we'll just quickly do a quick spin around the solar system and a little bit beyond, and then we'll start, we'll get to the nitty-gritty. I'm not quite Patrick Moore or Chris Lintott when it comes to interviewing, but I do a good job.
Hey, last time I was interviewed by Chris, I had to stand on a block because I wasn't tall enough compared to him. So it's much better this way.
I thought that what they did. I thought a phone book, but well, I'll be damned.
I hear Maggie keeps him well under control during the shows as well.
Yes, reins him in. He's a wild boy.
Okay, so it's been a fun week, astronomically speaking. Mm-hmm. Some interesting stuff in the sky. I'm going to cover something on the moon a little bit later, but I'll let somebody else take over at this point.
There's not so many planets on view apart from Mars this month. Like Jupiter's going to be very low on the horizon, and the same with Saturn. Uranus actually this evening, but it's going to be past obviously, is it's visible near Mars, but it's been moving along. It was like 21 degrees from Mars on 1st of March, and now it's 37 degrees. And the night of the 16th was the best night because of the thin crescent moon, and it was just above it, only 4.9 degrees. And I forgot to go and look at it. I missed it. Anyway, so then March the 20th, which is Saturday, isn't it? It's the official beginning of spring. Mm-hmm. Nothing much else planet-wise then. So it's Pollux on the 23rd of March is 5 degrees from the moon. So that should be a nice view. Beehive cluster on the 24th of March will be 4 degrees from a 75% moon. So these would be nice, you know, you could get them in a binocular field of view, or great for a shot photograph. Regulus on the 25th of March will be only 3.3 degrees below a 91% moon. Now, I don't know how well you'll see that because the moon's going to be very bright. And then March 28th is a supermoon. I think it's called the worm moon this time. Clocks go forward. Yeah. Check that out Saturday. March the 29th, Spica will be 5 degrees from a 98% moon. So again, the moon's going to be bright, but they'll be in the same binocular field of view. And that's really it. Yeah, nothing much going on other than, you can look at the stars, but not so much the planets this time.
If you're a lunar observer or imager, this week from about March the 15th through the 21st, it's lunar days 2 through 8. Now, the highlight really is going to be the Apennine mountain range. Now, using the Sky and Telescope field map, the reference is at NW/G9. That will be viewable from Sunday evening. So, of course, the Apennines is the most spectacular feature on the moon. It's formed about 4 billion years ago, and it was from the direct result of an impact that created the Imbrium Basin. Mountain ranges on the Earth obviously take millions of years to form. However, the magnificent ranges that surround Mare Imbrium were created in a matter of minutes. They're basically created by the shock waves that exploded out from the original Imbrium impact. Now, obviously, the Apennines stretch out about 370 miles, and it's about 3,000 peaks, of which the highest peak is Mons Huygens, which stretches from its base to its summit at an incredible 18,000 feet. Possibly the best skiing in the solar system. And of course, also in the Apennines range is the striking Hadley mountain, Monte Hadley, and the Hadley Delta. And that was the actual where Apollo 15 landed. So it's a really lovely place to image. I did actually image it. I did post about it in Astronomy Ireland because someone was talking about it. And if you really want to get up-to-date stuff on what to look for on the moon, I do recommend Googling Andrew Planck, What's Hot on the Moon Tonight. It's a cracking series of blogs. I post them on my Facebook. I post them in a lot of the groups because it really does help you find what you're doing. Apart from that, also there's some very good atlases. To be honest, the best ones is one of the better ones is the Clementine Atlas. I do recommend John Moore's set of 4 books on the moon, on its craters, irregular mare patches, and he actually even did one on the far side. And if you really are moon nuts, get Luna Cognita, because that is a splendid set, 3 books. It's published by Springer, but I find it a good reference. And, of course, anything by Patrick Moore on the moon. A lot of it's out of date, I know, but to give you a feel for how we got to where we are in regards to the moon today, he really does fill in some of the backstory, both scientific and otherwise. But so that's my little piece over. So, Kim, would you like to tell us about yourself, please?
Sure. So I work at the University of Leicester as part of the UK Swift Science Data Centre. So Swift is a NASA-based mission, was launched in 2004, and I've been working for the team since before it was launched. So it's been a lot of fun seeing the mission progress from launch to where it is today. Before I worked for Swift, well, basically I went to the University of Leicester as an undergraduate and I stayed. So undergraduate, PhD, working there, they can't get rid of me. We do actually joke that there's a black hole in the basement of the physics department because a lot of people who come here just never leave. Something is keeping us here.
Sounds like a wonderful place.
I do know one of the people who's teaching astronomy there, Paul Abel. He really does have the knack on how to teach the subject.
Mm-hmm. The scary thing is Paul was one of my tutees when I was doing my PhD. I actually had to do seminars when he was one of the students in the group.
Wow.
Mm-hmm.
Well, as I say, I get the Mercury and Venus newsletter, and he does for the BAA.
Mm-hmm.
And I found that I really recommend, if you're into astronomy, join the BAA, the Popular Society for Astronomy. Even become a friend of the Royal Astronomical Society, because if you're listening to these podcasts, there's a lot of stuff there in their journals that will really, really help you and keep you enthused.
Or you can get a membership.
Memberships are there, yes. They're worth having.
Definitely.
People say that the BAA, POP, and RAS are expensive.
Mm-hmm.
But for what you get out of them in regards of journals, in resources, it makes every penny worthwhile. And, of course, they are always publishing articles about everything to do with astronomy, physics, cosmology. So you want the latest information, this is where you need to go. Could you tell us a bit more about the Neil Gehrels Swift Observatory?
Of course. So it was designed to detect and follow up these things called gamma ray bursts, which are the brightest explosions in the universe since the Big Bang. So GRBs have been known of since the 1960s. They were actually discovered serendipitously. The Americans were wary that the Russians were violating the Nuclear Test Ban Treaty, so they had their Vela satellites looking out for unexpected flashes of gamma rays. Turns out they found some, but they realised they were not nuclear bombs being illicitly tested, which is good. But they couldn't tell at the time whether they came from our galaxy or if they if they were cosmological, so from throughout the universe. And it actually took 30 years before one of them could be localised well enough to realise that, yes, they were from well outside our galaxy. They're some of the most distant objects that we know of. So some of this stuff was known before Swift was launched in 2004, but the Swift satellite has, pretty much revolutionised what we've done with what we know about gamma ray bursts. So it's the really cool thing about Swift is not only does it detect the initial burst of gamma rays using its BAT, the Burst Alert Telescope, but then it works out whether it's safe to point the narrow field telescope. So there's an X-ray telescope and a UV optical telescope on board as well. And it works out whether it's safe to point those in the general direction of the GRB so we can get more data quickly. So we usually get this follow-up about 1 to 2 minutes after the GRB trigger. Whereas before Swift, it would usually be, at least hours, maybe even days before they could do a follow-up of the initial gamma ray detection. So Swift has completely opened up that parameter space and shown us what happens in the first few minutes after one of these triggers. The actual burst of gamma rays, that you can see from any of the satellites that follow it up, but all the other satellites could then say was, if they looked at the X-rays or whatever, you could just see that they were fading, probably fairly monotonically, so just fading away, sometimes suddenly fading more steeply. But Swift has shown that if you get on quickly, there's usually a very steep fading bit before it slows down, and then it may get to the stage that was previously seen, and then it might get steeper. And sometimes there are flares where it brightens as well. So all of that stuff was really discovered by Swift because we can get on so quickly within that 1 to 2 minute time frame.
I understand, and I could be wrong in this, but I'm sure you'll correct me, that they've actually used Swift to tie neutrinos to a star-shredding black hole.
We found there was a neutrino event that we showed was related to an active galaxy, which might be what you're thinking of. Mm. So yes, so there are all kinds of various neutrino detectors on the Earth these days, and so IceCube, for example, is one of the ones that's down at the South Pole. And usually, if a neutrino is detected, an alert will come out and Swift will follow up the position or whatever, but quite often they're large areas of the sky. So we, it takes we can only see a bit of the sky at any one time, obviously, and we sometimes do this, what we call tiling, to cover larger areas. And usually if there's a neutrino event that we follow up, we don't find anything that's obviously an outburst or doing anything exciting, quite frankly. I mean, known X-ray sources that are just burbling away at their normal level. Yeah. But in this case, I can't remember the name of the source, TXS something or other. They have such memorable names, these sources. But it was found that there was this active galaxy that was... it was in the right area, and it was shown to be brighter in X-rays flaring compared to what we'd seen previously. And so bringing all the information together, this implied that this really was where the neutrino had come from.
Amazing.
It is. Could you explain how Liecester is tied into the actual Swift project?
We were actually involved in as I mentioned, there were 3 instruments on board Swift, the gamma ray one, the X-ray one, and the UV optical one. And it's the X-ray instruments that we were involved in with before launch. So the X-ray detectors, so the detector that actually reads the X-rays, that was some of the work that was done at Liecester. And we were involved with other bits of the X-ray telescope in general, really. So that was pre-launch. And then obviously everything was integrated, stuck on the spacecraft, went up into orbit, and thankfully worked as it should. And now we do most of the X-ray calibration. So in order to understand the science that you're getting, you need to know that your instrument is well calibrated. So if you get the detection of an X-ray photon at an energy of 10 keV, I'm using the units keV there. That might not be familiar to everybody. EV is electron volts, and it's a unit that gets used a lot in X-ray and gamma ray astronomy. Basically, we need to know that what we're measuring is the actual energy that is being emitted from the source. So that's where the calibration comes into things. And we also run the UK Swift Science Data Centre, which means that we are one of 3 data centres which provides Swift data. So another cool thing about Swift is the data are immediately public. So as soon as we observe anything, once the data are on the ground, which will be usually within a couple of hours, anybody can just go and look at these data and do what they want with them. And so we make all these data available on our website. We offer training sessions in how to run the software to analyze the data. We have an email help desk. I get random questions to that, believe me. That's so we're Leicester is well and truly in the middle of things.
Now, I understand that what Swift can do is it can also then tell Earth-based observatories where it is,
yes,
so that they can do optical follow-up on an observation.
Mm-hmm. The data from Swift come down very quickly. So if we get a new gamma ray burst detected, we will get alerted to it within a few seconds. And some of the information goes out automatically. So we have this system called GCN, which stands for the Gamma Ray Coordinates Network. And the information gets sent out to the GCN system, including to things like robotic telescopes. So some telescopes are set up so that they can follow a GRB trigger automatically. Other ones require a human to jump in and say, stop doing the observations you're doing, look at this instead. So those are override programs for some of the bigger telescopes. But yes, we look at the data as soon as it comes down, as soon as they come down, and confirm that it is real, and then make sure that all the information is sent out as it should be, so that anybody who, be it with a huge telescope in Hawaii or Chile or wherever, or somebody in their back garden, the coordinates are there, so anybody can go and have a look.
I do a lot of robotic imaging, remote imaging, really. And it's very easy to get hold of the RA and DEC, and if there's a scope available, to get an imaging run done there. Mm-hmm. And I do understand that you've also the Swift's also worked in alongside LIGO and Virgo back in 2017, I think. Yes. It was October.
It was August. Believe me, the date is seared into my memory. So for people who may not know, LIGO is the Gravitational Wave Observatory. It's a laser interferometer gravitational wave observatory. And since 2015, the advanced version of LIGO has been looking for and detecting gravitational waves, and advanced LIGO came online in 2017 as well. And there have been lots of these gravitational wave detections, and Swift followed them up. I mean, they give enormous areas of the sky. The error region from a GW detection is huge. We call them error bananas usually because they tend to be kind of banana shaped. It's quite amusing, really. But it takes a lot of Swift pointings to try and cover one of those. And I mean, it's not just Swift, obviously, everybody looks, but for the first couple of years, there were lots of these GW detections, but we didn't detect anything in the X-rays or the gamma rays that could be tied to one of them. And then on the 17th of August, 2017, there was a LIGO trigger. And then I think it was something like 1.7 seconds later, the Fermi gamma ray burst monitor, so that's a different GRB mission, but Fermi detected a gamma ray burst that was coincident in direction for this. Swift didn't at the time because it was the other side of the Earth. This stupid planet getting in the way. But once we, everybody thought, oh, look, we actually do have this gravitational wave and a gamma ray burst that we think is almost certainly related. Basically everybody and their dog who had a telescope was looking at this. And we found so this was the UV optical telescope on board Swift. We found a new ultraviolet source. It's known as a kilonova. Yeah. And we detected that just shortly after the optical counterpart had been discovered. And it was amazing. There was so much data on this event, and it was all brought together. And sadly, it's still the only gravitational wave event that we have an electromagnetic counterpart for. So we're hoping there will be more when LIGO gets switched back on again, though that won't be till 2022, actually.
I was going to say, don't they believe that the event on August the 17th was possibly a collision of two neutron stars?
Yep, absolutely, it is. So we expect to detect gravitational waves either from colliding neutron stars or merging black holes or a black hole plus a neutron star. And it's the merging of the two neutron stars that we would expect electromagnetic radiation from, as we found. So you get a corresponding gamma ray burst, specifically a short gamma ray burst, because there are two types of GRBs, short and long. Short are the merging neutron stars. The long ones are known as collapsars, which is when a really massive star basically collapses in on itself and forms a black hole and shoots out jets of radiation as it does so. But these short GRBs should lead to detectable gravitational waves. And in this case, we saw them.
Mm-hmm.
The really nice thing is, I'll post a link into the show notes for this. On the NASA website, there is a Swift gamma ray burst table, which is generally updated at about one business day. The Swift BAT enhanced data product catalog, normally they update within 2 weeks.
Also, on the Liecester webpage, we automatically create X-ray light curves as soon as we get the data for every gamma ray burst. So that's done within hours, and so you could see how the X-rays are fading or brightening or whatever fantastic thing that specific GRB is doing.
One of the nice things about the Swift page on the Liecester website is you have a Swift-XRT products page that lists all the GRBs, their catalogue stuff, their positions, the light curves, everything.
Yep.
Yeah, as you can probably guess, I have been really totally geeking out and going through this.
So I should give a shout out. Most of the work for that was done by my colleague Phil Evans. I mean, we all test things and stuff, but the real nitty gritty of the software writing behind that was Phil's work, and it's amazing. It's so much easier. I mean, we all know how to do it by hand as well, so I can run the software and create my own light curves and spectra and everything. But this is done so quickly and so automatically. It's made everything so much easier, because if we have lots of GRBs detected, over a few days, we have to work out which ones are more interesting to follow up or which ones are the brighter. And these automated products make it so much easier to differentiate between the more interesting ones and the interesting but not quite so interesting ones.
Since 2004, have you noticed any type of actual pattern?
No, I wouldn't say any pattern at all. So, so SwiftBat has to date discovered or detected 1,441 GRBs. Just to get that number in there, I'm sure it'll be updated sometime soon. They are basically scattered all over the place. We have lots of long bursts, not quite so many short bursts. We can see a lot of them show a sort of similar fading in the X-rays. So we have what we refer to as a canonical power law, a series of power law decays, though none of them are all that identical, quite frankly. But there is a typical steep, flat, a bit steeper again pattern. But that's really the only thing that is particularly similar between them or any pattern that we could actually see.
How common are they?
The thing about gamma ray bursts is we only detect them if the jets of radiation are pointing towards the Earth. So they don't give out the energy the same in every direction. They are literally jets. And they're fairly narrow jets as well, so they have to be pointed fairly well towards the Earth and Swift for us to detect. So on average, Swift detects about 90 a year, but we expect that there's one going off every day if we could actually discover them all. Yes, yeah.
Oh.
90 a year, that's what, 2 a week? That's pretty amazing.
It is. I mean, you say 2 a week. We've actually had 5 in 24 hours before now, because they are totally random. I mean, you can go weeks, a couple of weeks without any, and then we start wondering if the guy who's in charge of the gamma ray instrument, Scott Bartholomew, we call him Batman, obviously, because it's the Burst Alert Telescope. If it goes for more than about a week without anything being discovered, we start wondering if he's been turning down the sensitivity so that he can have a break.
Have a break or go on holidays and not worry about it. Yeah.
Exactly.
Not worry about it. You might call then, like 24/7.
Yes. Yeah. I mean, so taking Leicester as an example, we are on call the 24/7, but for 2 weeks in 5. So in fact, our most recent duty week started today. I'm hoping something will happen while we're talking. If it does, my phone will beep and we will know straight away, but nothing yet, I'm afraid. For that week, if anything goes off, then Leicester are in charge of the, this week we're in charge of the X-ray analysis. The other week that would be on call, we're as well as in charge of X-ray analysis, we're what's called the burst advocate, which basically means you advocate for the burst. So, you are the point of contact for a GRB if it goes off in the time when you personally are on call. Leicester are specifically involved with the X-ray telescope. The UV optical telescope has a UK group down at MSSL, the Mullard Space Science Laboratory, which is part of University College London. So they are specialists in the UV optical stuff. The gamma ray people are all in the States, and the X-rays, as well as us in Leicester, there are groups in Italy and the States as well. Likewise for UVOT, there's another group in the States. But when we're the burst advocate, that basically just means every burst has a burst advocate, because you need a point of contact so that if somebody with data from another telescope says, would you like to include this in a paper you might be writing or whatever, it needs a point of contact, and that's what the burst advocate does.
Okay, that's so interesting. I'm blown away.
Well, to be fair, I'm still blown away by it all, and I've been working on the mission for 16 and a half years, so...
Must be incredibly exciting, though, to have the fact that you could actually notified about a gamma ray burst.
It is.
So
fast. Yeah, it absolutely is. I mean, okay, so when it's 2:00 in the morning and you have to get out of bed and look at the data, it's slightly less exciting, but there's still the underlying excitement, and I get accused of being far too perky and excited on a telecon in the middle of the night, apparently. Obviously there's still my underlying excitement that's shining through, shall we say.
I've just been going through the website looking at some of the images attached to some of the actual entries. It's really fascinating looking at them. Looking at GRB 21022B, the fact that we can actually see exactly where the GRB came from, I think is really fascinating. And of course the light curve. That was really interesting to see.
Yeah, I mean, it's fantastic stuff. It really is. There's so much information that we can get, even from a single one of these GRBs. I mean, obviously, for some of them, we get more data than others, depending on how bright they are or whereabouts in the sky they are, because some places are easier for Swift to observe than others. But yeah, we have some amazing data sets.
Looking at one of the graphs, particularly on this particular one for the light curve, the count rate was from between 0.5 to 10 keV after the trigger happened for BAT. Seeing that information is really great. Sorry, I'm really, really enjoying the website as we do this show.
I am very glad that you're appreciating it. We put a lot of hard work into that website.
As I say, I do a lot of imaging. I put all my stuff up on Facebook quite often, and it's looking at the stuff behind what we can see in the optical. I think really makes you appreciate it even more so, because this is the stuff you don't get to know unless either you're into astrophysics and cosmology, or it's just you pick it up from television, watching Horizon, Sky at Night, or even PBS. but to actually see some of the actual hard data, it's blowing me away.
Well, I am very glad that we can help you to geek out in this area.
I grew up reading Kip Thorne, Susskind.
Hey, I've met him, Kip Thorne.
Oh.
I've got books by the Indian physicist I can't even pronounce it tonight. Chandrasekhar.
Chandrasekhar.
Yes.
Yes.
Thank you. I nearly got there. I read those books at work just to keep myself from falling asleep. Most people tell me that if they were reading it, they would be asleep. But one book I will recommend, if you listen to the show and you want to know more, go get Black Holes and Time Warps by Kip Thorne. It's thick, it's meaty, and he's kept it dead simple.
Yeah, I agree.
For a long time, it was my nighttime reading for the final relax before sleep. I'd open up and I'd read a chapter of Kip Thorne.
Yeah.
Neil, you've been very quiet.
Yes, I've been listening with great fascination. How long will the mission last, Kim? Or is there going to be a replacement as well? Is that in the pipeline?
Swift has no consumables on board. It doesn't have any fuel or anything for whizzing around. It just has spinning gyroscopes and the solar panels. So there's nothing that will actually run out in that respect. I mean, there's obviously the possibility of it getting walloped by a passing meteor or something, which would be a shame. But the only real eventual problem is atmospheric drag. So we can't boost it up back into a higher orbit because there aren't, we don't have jets on board to do that. But currently, the predictions for how the solar wind is affecting our atmosphere says that Swift should be stable in its orbit for the next 10 plus years. Wow. Generally, in that case, the issue will actually be funding. However sad that seems to say, eventually NASA or the UK Space Agency will probably just say, well, it's an old mission. We're not going to give you any more money. Obviously, we don't want that to happen, and it isn't happening at the moment. I hope if anybody from the UK Space Agency is listening, please extend our grant. It runs out at the end of this month. So in that respect, it will stay up for as long as everything is functioning. There are future gamma ray missions that are coming up. There's SFOM, which is a French-Chinese mission. That's going to be a gamma ray burst chasing thing as well. There are other missions that can do similar things, though none of them are quite what Swift is at the moment. We would love to have a Swift Mark II, but you can't get funding for everything, unfortunately.
No.
I think one of the things this does actually do, I think it shows how good UK space is, and the fact and how good the institutions are which are actually running these projects. I know in the world everybody's after the same funding and everything else, and to get instruments on board everybody else's satellites. But I have to admit, and I know this was something that Patrick brought up in one of his shows back in the 80s, just how good our universities are when it comes to delivering not only the science to run the mission, but to actually build, to actually create and build the instruments.
Absolutely. I mean, Leicester we have what we call the Space Research Centre, which is basically the part of the physics and astronomy department that does the designing and building of space hardware. There's been something that Leicester has built operating in space constantly since the late 1960s. And we're just one institution in the UK. So yeah, it's amazing. I have some wonderful colleagues in the Space Research Centre who build the most fantastic things, and they keep operating. I mean, Swift was designed as a 2-year mission. Let's hope it lasts for 5 years, and we're at 16 and a half.
Yeah.
So, they absolutely, well, I don't want to say over-engineer because that sounds bad, but they do it so wonderfully that these things last so well.
Well, I was just thinking about that because Prospero, which was the very first satellite the UK put up, is still in orbit. It still operates. The frequencies for it have been given to somebody else. But I know that a few years ago, they actually tracked and confirmed that the satellite was still in operational condition. So Swift just shows us how good stuff is getting built these days.
Yeah, absolutely. Though these days, any mission that is launched has to have a time frame to be able to deorbit it, because obviously we're having the issue with there's an awful lot of space junk up there. And you have to have a way to make sure that it won't just hang around forever, getting in everybody's way.
Oh, yes.
So, even though these things do, keep operating for a very long time, to some extent, eventually they're going to have to be brought back.
Anne?
Yes.
Anything you'd like? Any other questions?
Oh, I was just wondering, they don't seem to come from the Milky Way, do they, the gamma ray bursts?
That's correct, yes. So, in fact, they are seen in some of the most distant galaxies that we know of. It is not expected that we would ever detect an actual gamma ray burst in our galaxy because we don't have the right environment. You need, if it's for the long GRBs, which is what you would expect in a star-forming galaxy like our own, you need really massive stars. But more to the point, it's the actual environment. So the metallicity. So as you may know, astronomers are very odd in that they call anything that is heavier than hydrogen and helium a metal. Don't ask me why. It's just one of those things. But you need low metallicity environments, and the Milky Way has too many metals for it to have stars that would form gamma ray bursts. So we would never expect one in our own Milky Way, which is actually probably just as well, because it's likely it would be really quite unhealthy for us if the jets were pointing towards the Earth.
That was going to be my next question. If it never came near us.
we wouldn't want one, quite frankly.
No.
There are similar events in that, they're called SGRs, which stands for soft gamma repeaters. And as you might guess from the name, this is something that repeats in the gamma rays. But if you only see it once, it can actually appear as a short gamma ray burst. But SGRs are typically found in our galaxy. And although when Swift first triggers on a gamma ray burst, we don't know the distance to the object. So if it's a short event and its position is fairly well aligned with our galactic plane rather than way out of the bulge and away from the galaxy and so outwards, and then we would typically guess that it's an SGR and therefore is within our galaxy. Though there are also some SGRs that are They give out giant flares, and those can actually be seen out to nearby galaxies, which is something that Nick was mentioning to me earlier, in fact. Nick, did you want to mention a bit about that?
Yeah, well, we can do, I suppose, really, because I was reading the story earlier, and I did actually PM you about this, because
yes,
this is, I'm just getting back into the story now. It's a GRB 241-5A, and it was captured close to our home galaxy, and it was a rare stars giant gamma ray outburst.
Yeah, so in this case, it actually was one of these SGRs. We thought it was a GRB initially, but it actually isn't. So this, as I said to you earlier, it's not. This is not an object I know a vast amount about. It's not something that Swift actually triggered on, but it's just a really good example to show that you can't always tell what the object is until you get a bit more data, because these short gamma ray bursts and these SGR giant flares can look really similar, but they are totally different events. So these SGRs are actually very magnetic neutron stars. So it's not the merging of two neutron stars. It's not the death of a massive star. It's just a very magnetic neutron star. And we think that the gamma ray flares that we see are due to the instability of the magnetic field. And there are far fewer SGRs known than there are GRBs. So in some respects, that makes them more interesting.
And what people don't realise, they can actually disrupt mobile phone reception on the Earth, as well as being messengers from the very early history of the universe.
Yeah.
Just to give people an idea, basically, in relation to our star's a very ordinary one. When it dies, it will get bigger. It will become a red giant star. And after that, it will collapse to a small compact star called a white dwarf. But these stars are much, much more massive than the sun. So they have a different end game in life. Now, basically, when these massive stars die, they explode into a supernova. And then you've got something that's left. It's a very compact star, and you can probably fit into a valley about 12 miles across, 20 kilometers. It's a neutron star. So that's where the really giant stars go. When they go supernova, eventually they'll end up as a neutron star, and which has been described in some respects as the black sun. That's one of the descriptions.
Black suns is something I just looked at as well. And
yeah.
Anyway, I'd love to hear all of your thoughts.
The interesting thing is, scientifically speaking, black holes were predicted, I think, in the 18th, 17th or 18th century originally. It was really Schwarzschild who mathematically proved them, because Einstein didn't want to believe in black holes.
Yeah, very true.
Yep. And of course, everybody goes on about CERN, they're going to create a mini black hole, it's going to eat the Earth.
Yeah.
Unfortunately, even if they did, the life's time of a mini black hole from CERN is 40 minutes, 42. That's why it's the meaning of life, the universe, and everything. They can't feed. They just go poof into Hawking radiation.
Yeah, black sun, something I just saw about myself, this week. And I think that's something incredibly interesting too.
Yeah. Well, it was interesting that they were first discussed back in the 17th or 18th century. They were postulated.
Yeah.
Who was thinking about that, Nick? Sorry, I just put you on the spot.
I don't remember, but I do know it gets mentioned in Black Holes and Time Warps. That's probably most of the reason I actually remember most of this stuff. Also, I think it was touched on in Suskins on how I won the black hole war with Hawking and made the universe safe for everybody.
Oh, yes.
Yeah. Kim, you were talking a little while ago about this space junk up there. And of course, I instantly thought about Starlink.
Me too.
And I noticed that tomorrow, a Starlink is going to pass within 1 kilometre of the Swift satellite, travelling at 9 kilometres per second. Are they worried about the chances of, or is there anything you can do? Can you move it out the way to keep away from Mr. Musk's rubbish?
Okay, so no, we can't. We have had warnings of nearby things. We basically hold our breath. So yeah, if something were to collide with Swift, there is absolutely nothing we could do about it. And over the years, there have been times when we have had, I'll say close calls, but that's because we get told it's expected to come within such and such a small distance, and then usually it's not quite that bad. And obviously nothing has hit us yet. No. But it is always a concern. It absolutely is.
Is Swift in a equatorial?
It's a low Earth orbit. So every 96 minutes, it is. Well, I could give you the actual degree of the tilt if you wanted, but
go for it.
Nah. What I was going to say is it never comes far enough into the northern hemisphere for it to be seen from UK skies, sadly. So southern United States or southern Europe, you can see it, but not from up here, sadly.
The space junk is an awful worry, though. They're just putting more and more up, and stuff I know comes into the atmosphere and falls down. But the giant claw that's meant to come in 2025 is not going to be enough.
Mm. It is a concern.
Well, the important thing is, Susan, a lot of this stuff is tracked on a regular basis.
Yeah.
If you remember, we had the Earth suddenly acquired another moon, which everybody was getting all gooey and happy about, and then it turned out to be a Centaur rocket stage.
Yeah. Kim, is there any way you can turn the satellite to protect it?
The only thing that we can command Swift to do is to slew around in its orbit. So we can't say, right, move 2 kilometres that way. We can, we could rotate it so it was edge on, as it were, but it would never be enough. If something were going to be that close, Nothing we can do, sadly.
Still, when we think of the amount of space debris, when you see depictions of it, it all looks really close, like the way the asteroid belt looks really close, when they're not that close.
No.
So there's plenty of space.
There is, yes. As long as you go through the gaps between everything, you're fine.
If you were able to design a mission for GRBs, what would you want to do with it?
Oh, nice question.
So there was hope at one point that we could have something like Swift, but as well as having the gamma ray, optical and X-ray instruments on board, also have something towards the infrared. Because, well, obviously the more wavelengths you can cover, the better. That sadly never actually happened, but that was a hope. What we would really like is a mission that can immediately give you a redshift, so the distance for anything. But then again, you do need to be able to detect an optical afterglow to get the redshift, and the UV optical telescope on board Swift actually only detects about a third of all GRBs that we follow up quickly. It depends whether I'm allowed to, wave a magic wand and have absolutely everything that I would like without knowing how we could do it scientifically. In that case, we would have multiple Swifts around the orbit, so we were covering the whole of the sky, because the bat can see about a sixth of the sky at one time, about the same as you can see out of one eye. In fact, one human eye is about what bat can see. So if we could have them positioned around Earth's orbit, all moving together, so we could cover all of the sky, and then we'd have the gamma ray instrument and the X-rays and the UV optical and the infrared, and something that would always give us a redshift if we detected things. And that would keep me quite happy.
How many would you need, in fairness?
Well, I guess at least 6. Yeah, maybe a bit more, so you have a bit more overlap. Say 8.
Oh, wow. I mean, start with 6 and move up,
Yeah, just keep adding one every few years.
Keep adding one every few years.
It sounds like you need something like the Comet Interceptor mission that the European Space Agency is putting together.
Well, I mean, as you know, Neil, yes. Swift does observe comets as well.
Exactly. Yes, I did mention it because it the interstellar object, Mr. Borisov's comet. Yes.
Yeah, we're observing Comet 141P Machholz 2 tomorrow, if that means anything to you.
It does.
And I think Don would be very, very happy to hear that.
Yeah. It's a comet that's disintegrating as it's, disintegrating rapidly, I believe. Fascinating.
Well, yeah, because the interesting thing, I think the last satellite to observe a comet was IRAS. And we're going way back then into late 70s, early 80s.
Yes.
And I think it's great that Swift is doing this because it can provide information that we just can't get with ground-based instruments or with the Hubble. So, all power to Swift, the fact it can do this.
Yeah, I mean, it takes the science. So we have the people who work for Swift. We have science planners who put together the actual science plan for each day. We have the Observatory duty scientists, the ODS, of which I am one. And we have all these people in the background, and there's been so much amazing software written to be able to do things like observe a comet which won't stay still, for heaven's sake. I mean, it's much easier to observe something that's relatively speaking, stationary, rather than something that's whizzing through the solar system and, in and out of your field of view before you blink, kind of thing.
Yes.
So there is a huge amount of work that has been put in by people over the years to enable us to be able to observe the comets. And we get some amazing data because of it.
It must have been amazing trying to get the Borisov comet because it's interstellar origin. It's going through even faster than a normal comets.
Yes. As I said, it's much easier when things are a long way away and don't appear to move.
That's it.
I was really looking forward to this, and this show has really been great. I'm enjoying it tonight. It's brilliant.
Excellent.
That's all I can say.
That's great, Nick.
Nick loves all this technical stuff, don't you, Nick?
Oh, absolutely, yes.
Would you like to talk more about the telescopes? Because you're the man for the techniques. I mean, I'm a comet person, and we've got to the Macault's comet, and after that, I'm a little bit lost with these gamma ray bursts. Kim, your phone hasn't gone off yet.
No, I'm sorry, it hasn't. Absolutely nothing.
Oh, you see.
Right, honest to God, till like a couple of days ago when I knew you were coming on the show, Kim, gamma rays were the Hulk to me, and that was my major information. It's incredibly interesting, and I have to say I've absolutely loved reading about the whole lot. I just think it's fascinating. I mean, it must be an amazing job you're doing. I mean, obviously you're doing it since 2004, so you must like it.
Yeah, absolutely. Yeah. It's. I mean, the Swift team are such a lovely bunch of people. I mean, science aside, we call each other Swifties, obviously. Yes, the Swifties are a lovely group, and they really are.
And I hope how long it keeps going and no junk gets in your way in the meantime.
Thank you. I think we all hope that too.
No, I really do, because I do have a thought in my head a lot about the junk up in space, and it worries me. But maybe that's because I'm a mother and I'm an Irish mother, and I worry about dirt.
Like Mrs. Brown.
I am Mrs. Brown in some ways, but yes, you need to move the dirt out of the way so we can get the good work done, And there's an awful lot of dirt up there, and nobody's cleaning it. It's like an attic that nobody goes up to. People keep putting stuff up into it, but nobody's cleaning it out. So as a mother, I think it's my time to say somebody needs to get up there and clean out that attic. You can't keep putting stuff up there unless you're willing to, clean it out first. But that's
the interesting thing is that the interesting thing is they're actually testing various ways to deorbit this stuff. They're trying nets, harpoons. I think one possible solution was a space tug that would just nudge the errant piece of debris into the atmosphere to burn up.
I mean, I would be happy to be launched into orbit with a large net.
Absolutely, Kim, just go. I'd be the same. A large sweeping brush would be my thing, or a really, really good Dyson. Like a really good Dyson. I mean, we're going into a vacuum using a vacuum. I mean,
yes, exactly.
We must say, though, that other vacuum cleaner brands are available to purchase.
I mean, he does make really good hoovers and hair dryers, and other electrical products are available, of course. Somebody needs to clean up that stuff, and even the stuff on the moon that they're leaving, apart from stuff maybe we want to keep. But
like the odd golf ball, you mean?
Yeah.
You know what Neil Armstrong left there? In the movie, he threw something off into the distance. We don't know what it was.
Is it a picture?
I don't know.
An empty can of Coke.
No, it wasn't a can of Coke. I'm led to believe that it was supposed to have been a photograph of his daughter.
Photograph, yeah.
Kim, are you an actual observer yourself? Do you go home and have a telescope and have a look at the night sky or a pair of binoculars even?
I have binoculars, but it does these days it does have to be something really quite spectacular usually to get me out. I mean, if I'm wandering around somewhere dark, then I love to see the stars. But I don't have a telescope. When I was an undergraduate, I was obviously part of the Astronomy Society at the university. In fact, I was the president of it for a couple of years. And we used to have observing nights, if it was clear, obviously, each week. And the university has a couple of telescopes, as in actual domes rather than just the carry one around. We have those as well. Mm-hmm. And that was, I enjoyed that, but that was partly because we were, it was me and my friends were doing the observing. And I've just got so used to doing X-ray astronomy instead of optical astronomy. So I appreciate stargazing if it's a lovely dark sky, but I don't tend to go out of my way thinking I should really get my binoculars out and go and look at such and such a star or whatever. Not these days.
Did you see the comet last year? Comet Neowise.
I did, yes. I made the effort for that.
Yes, I have to mention Comet.
That was super.
If it's not a comet mentioned every 10 minutes, that's it. I get withdrawal symptoms. I'm starting to go downhill.
Oh, you're jonesing. You start jonesing, Neil.
Yes, Neil. Oh, dear.
I was just going to say to Neil, did you see that thing where Comet Shoemaker-Levy 9 crashed into Jupiter in 1994, and there's molecules of it still left in Jupiter, and they're able to detect them and measure the speed of the wind on Jupiter.
I will be talking to David Levy on Sunday, and Caroline Shoemaker. So actually, there's a bit of a hint there. Well, I've done a spoiler, haven't I? I've done a spoiler.
Yes, you have, Neil.
The news won't be released until Friday, but we're allowed to talk about it because this won't be going out till after then. But I sent you a big long thing about it there.
The Shoemaker Levy, it made new molecules. I mean, I read that myself, and that's amazing. I mean,
to discoverers on Sunday, so that would be very exciting, won't it, Nick?
Absolutely.
You can talk about that with them then, because that's actually help measure the speeds of wind on Jupiter. It's incredible.
1,450 kilometers per hour. Like, wow, up and near the poles in Jupiter. Like,
that's a bit like here last week.
Shoemaker Levy 9 actually explained a crater chain on the moon, the Davy crater chain.
Yeah.
That's right. Yeah.
And also the one on Callisto. So, as I say, if it hadn't have been for Shoemaker Levy 9, we would have still been relatively much in the dark about how certain crater chains actually formed. Was it Jim Scott? We definitely discussed this with Jim Scotty, because he did a painting of it.
Yeah.
And I know that we discussed this with David on many occasions.
Yeah.
About the fact that in some respects for the Earth, Shoemaker Levy 9 was really much a wake up call about how much stuff is out there that could potentially come our way.
Yeah.
Yes.
And of course, it kicked off the whole near Earth objects program to getting government support all around the world. But that's another show.
That's Sunday. Excellent. No homework needed then.
Yeah. I have got my copy of Shoemaker by Levy beside me right now. I'm doing my homework.
I haven't got one. I looked on eBay and they're like about £1 million or something. I don't know.
£1 million, wow.
I think so, yeah. They're about 1 million, 2 million, something like that. 2 million euros or whatever that is.
No, they're not that expensive, Neil.
Oh, I know. I'm probably exaggerating a tiny bit.
Yeah.
Tiny bit, yeah.
Tiny. So we're not buzzing tonight, Kim. I mean, it will go off at 2 o'clock in the morning today, won't it? So
quite possibly it'll wait until I'm fast asleep, having some amazing dream about something.
Do you have it on you right now, Kim? Yeah.
Sorry, what was that?
Do you have it on you right now, like
my phone? Yeah, I have my personal phone and my work phone are both sitting next to me.
Incredibly exciting, though. Just waiting. I mean, obviously, I know you said average 2 a week, but you did say there was 5 in 24 hours. Is that what you said? When was that?
Oh, so let's see, March 2008 we had 5 in 24 hours.
Wow.
So not the weekend that's just been, but the one before that we had 5 over the weekend, which admittedly is slightly, but annoying. The crazy thing is that was when our computers at Leicester had scheduled downtime that weekend. It's like the universe knew, because we are the ones who do that automated X-ray analysis that we were talking about before. And without our machines, people have to do it from scratch, and you get you get used to it just being done for you, and then when you have to go back and so the universe just knew that from that Friday to the Monday it was going to be busy, and it's been quiet since then.
You're saying it's 2 weeks out of 5 you do?
Yes, Leicester.
The other 3 weeks, do you still not just listen?
Oh yeah, absolutely. I mean, I don't get texts to my phone. We just switch those on for those weeks, but we get an email. The emails come through as well. So if I'm awake and connected to the internet, which most, if I'm at home, I always am, I will see a burst, it goes off. And quite often I will dial into the telecon, even if we're not on duty, because, I'm nosy.
Nosy, but I mean, who isn't? You just want to know, and I completely understand that. And I mean, that's a lovely thing to actually look into, rather than, say, an email from school asking you to.
Yes.
It's PE. I mean, it's a gamma ray. It's a gamma ray burst. Like, wow. Sometimes they happen at. So ignoring the ones that happen in the middle of the night, even when I'm awake,
now I'm not sure, one Christmas years ago, it went off in the middle of Doctor Who. It's serious. Well, not even in the middle, it was towards the end of the episode. Luckily I was recording it, so it was okay. But GRB interrupted my viewing of Doctor Who. So rude.
You know, I mean, how dare they, you know?
Yes.
It's a lovely thing to be interrupted by.
And was it a particularly interesting one?
It was actually, yes.
Oh, that's right. That's okay.
And it got referred to as the Christmas Day burst because it was when Doctor Who was on at Christmas instead of New Year, and there were papers written about it and all kinds of things. It was fantastic.
What year was that, Kim?
2011. So it would have been 11, 12, 25A.
You just beat me to it.
Oh, lovely.
Yes, so I forgave it for interrupting my watching of Doctor Who.
Which one has been the most special one that you've been
involved? Goodness, you can't make me make a choice like that.
What's your favourite child?
I mean, there have been, there are different GRBs that are interesting for different reasons. Obviously, there were the very first ones that we ever discovered. There's ones that I got to write a journal paper on, which makes them interesting in that respect. There was... I really couldn't put my hand on heart and say what my favourite one was. It was pretty cool, the first short gamma ray burst that we localised, though, because before Swift came along, no good, accurate position for a short gamma ray burst had been identified, because the afterglow, so everything that we see after the gamma rays, fades really quickly. For short GRBs, they're fainter and they fade more quickly, and so before Swift, none had actually been localized. So in 2005, when we first localized a short GRB and showed that it was coincident with a galaxy that would be consistent with it being merging neutron stars, that was pretty cool.
Wow. That was like a year after you started, was it?
It was about just over 6 months, in fact.
Oh, wow. Even less.
Yeah, we were off to a flying start at that point.
I'm looking at the information about the Christmas Day burst. Mm-hmm. It was 28 minutes long, at least.
Yes, it was a particularly long one. That's not normal.
And the afterglow in X-rays was about 2 days.
I mean, the afterglow in X-rays, some of them we have followed for months. I think, now what was it? Let me just check. I'm getting the right one here. Some numbers you remember. Yes, GRB 060729. So that means 2006, July 29. That one we actually followed for... let's see, 115 days, more or less, slightly more than that, actually, looking at that, because then we had a non-detection. But, I mean, we followed it for months and months, that one.
I know, because I was just reading that GRB 101225A, along with 111209A and 121027, they're seen as part of a new class, ultra long bursts.
Yes. To
do with blue supergiant stars.
Yeah, I mean, we still don't have a huge number of these ultra long bursts, but so for short GRBs, those last less than 2 seconds. Long GRBs, typically up to a few hundred seconds is normal for the gamma rays, and then you do get these ultra long ones that go on and on and on.
Yeah, it's interesting to note the Christmas burster. There's at least 2 possible hypotheses. Mm-hmm. One is that it was the binary system for about 5.5 billion light years away, redshifted at 0.33, and another one, it was about 7 billion light years using the Gemini North telescope.
Yes, this was one where we did actually get a redshift, a distance for it, so that was cool.
Yeah, it's as I say, I'm just reading this stuff up as we go along. I will put all the every page I've been looking at, I will put in the show notes. I promise everybody they will be there. Because this just looking at some of this stuff, it's really fascinating.
Yeah.
We've come so far so quick in some respects. When you think how long astronomy has been around, the history of gamma ray bursters, comparatively speaking, is new, but we've come so far in being able to figure out where they're coming from, what's causing them to some degree. It's one of those disciplines that really has jumped into overdrive to get to where we are now.
Mm-hmm. Yeah, absolutely.
There's even an animation from the Goddard Space Flight Center illustrating the two alternative explanations for the gamma ray burst. So I will put that link into the show notes.
If you're going to put links in and things, have you come across our Swift song?
No, I haven't, but please.
So
please sing it.
Oh, I'm not singing. Trust me, if you knew better, you wouldn't want that. But so there's an a cappella group in the States called Astro Cappella who write and perform scientifically accurate songs. And they're based out of the Goddard Space Flight Center. And one of them, Paddy Boyd, used to work for Swift. So obviously they wrote us a Swift song. So you should absolutely listen to it. It's got the proper science about GRBs in it, and it's ever so cool. And their songs are incredibly catchy. Actually, they're if you just look up Astro Cappella and have a listen, there the one about X-ray astronomy is my second favourite after the Swift song. But definitely have a listen. It's really fantastic.
They even have a CD out.
Sounds good.
Yes, they do. They also perform as the Chromatics, doing non-sciencey songs, which are equally good, but not so important for a podcast like this. But they're really cool.
Anne, Susan, any?
I know Anne wanted to bring up. Didn't you want to bring up the light thing?
The zodiacal light, yeah.
You know what? I'm glad you said it because I knew I was going to say it wrong. Anyway, go ahead. Zodiacal light.
Yeah, well, I was really excited about this because I only really heard about it only in the last few years myself, just from photographers sending me amazing photographs of this kind of cone of light that goes up from the horizon after sunset. And it's in the western sky in the spring and in the evening twilight in the eastern sky in the morning in the autumn. And so it's this column of light. It's tilted slightly at the angle of the ecliptic at the different times of the year. And for years, scientists and astronomers thought that it was just general cosmic dust from maybe comets and asteroids.
Yeah.
So the Juno spacecraft that was going off to have a look at Jupiter did a couple of flybys, gravity assist, and discovered it was actually getting hit by this dust on its way out and on its way back. And the solar panels on it, which are not dust collectors, but they turned into kind of accidental dust collectors. And they discovered that the one end of the dust ends at Earth, because when it gets to Earth, our gravity sucks up all the dust, and that's what we're seeing, this light, the sunlight shining up through it. But the other end of it is just out beyond the orbit of Mars. And they figured out then, Jupiter is the barrier, it's not letting any dust in, and equally it's not letting it out. So it's just orbiting around the sun, but in the orbit of Mars. So they deduced from that it's actually the dust that we're seeing, it's coming off Mars. Say, when you see a dust storm, there's very little atmosphere on Mars, so the dust storms can go up to I think it's something like 40 kilometers up, and that's enough for it to escape. And so all this dust that we see, this faint zodiacal light, it's nearly all Mars dust that we're seeing, which is totally new and just a serendipitous little piece of discovery by Juno, which wasn't its plan at all. It was going off to do something else altogether, and it discovered this. Yeah, so it's pretty cool. I was totally fascinated.
Yeah, I was too. And in fairness, though, I do think maybe we shouldn't have a Hoover or a Dyson for this. We kind of want to keep that dust.
We want to keep that lovely light, yeah.
We want to keep that lovely dust coming from Mars, which seems to have a huge amount of dust storms that are just all coming out. But leave it alone because they're all going into beautiful orbit and giving us beautiful light. But,
exactly, yeah. I just found it fascinating to think that it's completely changed our perception of the origins and the source of it, you know. Brilliant. Yeah, really great story. I loved it.
Pioneer 10, back in the 70s, linked the zodiacal light with the interplanetary dust cloud in the solar system.
Yeah. But didn't they think it was asteroids and everything being brought in?
Didn't Brian May, the guitarist of Queen, write his thesis on the zodiacal light? He did, didn't he?
He did, yes, indeed.
And I bet it's all wrong, isn't it? Oh, Brian, off you done.
Science, you're learning stuff all the time.
Yeah, he made up for it with some great records.
Yep.
But every day it's brand new. I mean, we learn, we think we know, we understand what we think we know, and then something else happens.
Yeah. The zodiacal light's also known as false dawn.
Yeah.
That's it.
Neil, do you have anything else you want to bring up about Swift?
No, that's it. I think we've covered it. We've done a wonderful show on it. I think we know everything there is to know.
You're right, Neil. That's it. We're done. We know everything. So
You know everything?
that's the end of the time-space continuum. We're sorted.
Yep.
Right at this moment.
We can start working at Leicester tomorrow.
Oh, boy. I think I'll just go back to my books in that case, Neil.
Hey, you want to go to Leicester, don't you, Nick?
Yes, it's on my list for when I go back to school.
There we go, Kim. You'll be able to see him walking through the corridors and run the other way.
I'll shut my office door and pretend I'm not in.
I really would. He's a funny fella. He's a funny fella.
Oh, thanks, Neil. This is about the best thing about everything. Everybody gets to have a good laugh during the show.
Absolutely. I presume we're not allowed to talk about the meteorite, no?
That big one.
Yeah. I mean, I was actually blown away by the scorch marks on the driveway.
Yeah, on the driveway in Gloucestershire, wasn't it?
Cheltenham.
I mean, imagine going out, there was a scorch mark on the driveway where it landed. Imagine going out to your driveway or out to your garden and seeing a scorch mark from where a rock landed. I mean, that is absolutely amazing. That just shows the heat it came down. I mean, a scorch mark on my driveway, I don't think I could actually get any more excited about anything ever. I would be beyond delighted, especially if there was a little rock there. I mean, to me, it's fascinating because it made a little scorch mark on cement. I mean,
they heard a thud during the night, but it wasn't until the next morning they found it.
Yeah, my driveway has nothing. It's so disappointing. It's just cement, and there's not even a car. Like, it's just... You know,
it flew right across Ireland, and then that amazing network of cameras that has been set up only in the last few years was able to triangulate and literally pinpoint practically that driveway. It was amazing.
Imagine going out and seeing a scorch mark on your driveway with it rocking it. Like, I mean, I'd probably just pick it up straight away, but I mean, you're not meant to. No. You're meant to leave it alone.
Somebody was asking during the week, they thought they'd found one, and they were saying, "Oh, we tried it with the magnet and we picked it up and all," and like the advice is, don't touch it with a magnet, don't pick it up, take a photo and get your GPS and then pick it up with tin foil if you're going to pick it up,
And then you're thinking 10,000 quid.
Just take pictures and invite the neighbours.
Yeah.
It's just amazing.
This is probably the best place to draw the show to a close. Kim, it's been brilliant having you. Thank you for coming. Thank you for putting up with us.
Thank you, Kim.
It was an absolute pleasure. I really appreciate the invitation.
And it was fascinating. We know a lot more than we did when we started.
Good.
So thank you so much.
Thank you, Kim.
So, as I say, what I'll do, Kim, one of our team will actually clean up the audio a bit, get rid of any pops and crackles and stuff, and I will send you a copy of the show if you wish. So you have it.
Absolutely. I'd love to have it. Thank you.
So I suppose the best to do is for everybody to say good night and to keep looking up.
From me, it's good night.
Good night, everybody.
Good night, Kim.
Good night.
And hopefully, Kim, you'll come back on a future date and tell us some more about what's going on with Swift.
I would be happy to.
Brilliant. Just keep looking up, everybody. The links will be on the YouTube show. I will put out an MP3 version in the Astronomy Ireland Facebook page.
Yeah.
So just pop along there and you'll get everything there. So have a good evening, everyone. Thank you for listening and enjoy. Good night, everyone.